Hi everyone, can you guys hear me? Please just type in the message box if you guys can hear me. Sorry, we've been having some technical issues. Okay, awesome. You guys can see the screen? Great. I'm very, very sorry we're so late. I do apologize. Welcome to the webinar, Rise of Robots. We'll get started immediately. Right, so what we're going to be covering is how robots are changing our lives, the transition from software engineer to data scientist, data analytics versus data science, and then we're going to be looking at a very short, small snippet of the code and how that correlates to the mathematics behind data science. Right, so effectively, in the last couple of years, we've been having a rise in toys and all kinds of household items that have turned into AI and robotics. Things like the Anki Vector, it's very similar to the Alexa, but it will time your cooking and it can help around the house. We've also got the Lynx, which is an extended version of Alexa. It's a humanoid bot. It has facial recognition. It can speak to you. You can speak through it. And I don't know if any of you have heard of all the creepy stories of Alexa waking people up in the middle of the night. But now effectively, they've given Alexa arms and legs. So lock your doors. Then in the world of prosthetics, they've also been using AI quite extensively to try and get the neural pathways to interact with the data science algorithms and the AI. If you look at this bionic hand, for example, this actually, has electrodes that picks up the electrical signals in the amputee's arm, and it then moves based on on how the amputee wants it to move. So it's almost like a real arm. And if you look at the Lynx down here, this thing is almost like the Jeep Wrangler of legs. The AI they've used here will actually navigate rough terrain for you, so it makes the walking experience more normal. Sorry, is this better, Etienne? Sorry guys, if my voice is distorting, just let me know. Is this better? Okay, great. Sorry about that. I think my microphone was turned up a little too loud. Okay, anyway. Right, so as far as robotics and AI is concerned, what they're doing now is, I'm pretty sure everybody has heard of the self-driving car. In Phoenix, Arizona, they've actually got a self-driving car called Waymo with an app, which is basically like a self-driving Uber. And you use the app exactly the same. You summon the car, it comes, picks you up, takes you where you want to go, and there's nobody in the front seat. So that's interesting. Then we've also got a new company startup called Neurala. They are using data science and neural networks to teach drones to pick up or to identify human beings. So if you're a person of interest for the FBI or in a police investigation or whatever, they send out this drone, and if they've got your photo, this drone can actually recognize you. Another interesting innovation that they're working on, they did a live demonstration in 2016, was with micro drones. This was the Department of Defense that did this test. They launched them out of fighter airplanes. And the whole point of this was to see if they could identify a target and surround said target. The nice thing about this drone swarm was the fact that they used a neural network. So they didn't program each drone independently. The drones actually worked like a hive. So if one drone got damaged and fell out of the swarm, the rest could just carry on going forward. Another interesting thing that I've found was this little bot called Atlas. This is a DARPA project. It's supposed to be a rescue bot. And the things that they wanted it to be able to do was drive a utility vehicle, remove debris blocking entryways, open a door and enter a building, climb an industrial ladder and traverse industrial walkways, and so on and so forth. The interesting thing about this for me was if you add weaponry to this thing, you're looking at Terminator. Although at this point it looks a bit like a robotic Jar Jar Binks, if anybody knows Star Wars. But effectively, this thing has shrunk quite a bit, and they're making a lot of strides with the algorithms to have the bot keep its balance. They were having issues with that quite a bit, and I know that it now has its own hydraulics, pumps and everything else, so it's now completely autonomous. All right. So how do you go from software engineer to data scientist? The thing about being a software engineer is you basically are working with data as you would as a data scientist. Software engineers, though, they will build an application that retrieves data from a user. It will then store that data in a database. You know, I'm pretty sure everybody knows how software engineering works. And then a data scientist or a data analyst will access that database and use that data to do their analytics. The difference between software engineers and data scientists is that data scientists use a lot of mathematics and prediction algorithms in order to give whatever company or whoever needs the reports to, sorry, just hold on one sec. Sorry, I apologize. The data scientist will do predictive modeling in order to take the data that the software engineer has accumulated and then do predictions for whatever company is looking for those predictions. The biggest step for a software engineer to become a data scientist would be the mathematics. A lot of jobs that you'll find will ask for some degree in mathematics or physics. And the reason for this is the mathematics is quite intense. It's not matric level type math. It's more university, depending on the extent of the data science you want to do. If you want to build the AI for robotics, you're going to need serious physics and mathematics skills. So depending on where you want to go, if you just want to do data modeling, basic mathematics is okay, linear regression and that type of thing. If you want to go into AI, I would suggest really getting into mathematics and really understanding how mathematics forms part of statistics and algorithms. So the difference between a data analyst and a data scientist, and there are quite a few memes out there saying that everybody's calling themselves a data scientist lately. The reason for this is because there's a very thin line between the analyst and the data scientist in a business. If you're working with AI and you're building self-driving cars and you're working in startups and building robots, that's one thing. You can definitely call yourself a data scientist from that perspective. But if you're working for a financial company, for example, you're more likely to do predictive modeling and some historical modeling as a data analyst would do. So data analysts basically just work with historical data. That's data that's already in the database, and they, or in Hadoop or wherever they will find the data, but it's already accumulated data, which they will then manipulate and do a report with, or do some sort of statistical model with. Where a data scientist can do the same thing, but they can take that that data and then do a predictive model, which takes a bit more mathematics than your average data analyst would have. Right, so two of the types of modeling that data scientists would work with, and it's not exclusive to data scientists, data analysts use this as well, excuse me, but you're most likely to work with things like linear regression and k-means. They each have, as you can read there, they have their own purposes. Linear regression is largely based on predictive modeling, and we'll have a look now at the mathematics of it and how to read a linear regression model. Sorry, I'm flying through this because we were late. I see I've actually just about done. So if you guys have any questions, I suggest you can start your discussions or have your questions in the chat area here, and the mentors can start helping you guys with that. Right, so I don't know. Yeah, Carisha, you will definitely be able to access the slides. It will be emailed to you guys. So with linear regression, you'll see on this side, or over here in the left-hand corner, you've got the code. This is basically just the code that will give you this linear line, okay? I don't know if you guys can see my cursor. If not, I'll try and explain as best I can. The math at the bottom here, this correlates to this little algorithm here. So first of all, reading a linear regression is pretty easy, especially if it looks like this. This is a very empty, clean model. The whole idea is that you've got your y-axis and your x-axis. Okay, so the x is at the bottom, y is your vertical. Then if you look at can you guys see my cursor at all? If somebody can just let me know. Not, okay. All right, so I'm going to try and explain this without the cursor. I apologize. Okay, so if you look at the purple line in the graph A, okay, and graph B, that line is your predictive line, okay? The dots in between, that is from data that's already been accumulated. So you've got your x-axis right at the bottom here where the independent variable is stated. And you've got your y-axis at the dependent variable. So your independent variable is a variable, let's look at farming. So your independent variable would be rainfall, okay? So if you've got rainfall, there's nothing you can do about rainfall. It's going to come, it's not going to come, whatever. Then you've got your yield, which would be the dependent variable. So let's say you're planting corn or maize. Based on the amount of rainfall, you can see that the yield will go up, as this line suggests. It goes up towards the higher end of the y-axis. Okay, stop me if this is not making any sense. and ask questions. I am watching the chat. So in historical data, these dots will be historical data, for example. So you'll know we've had, say, 50 tons of corn for X amount of rainfall. We've had 250 tons of corn for X amount of rainfall. Then you'll use the algorithm on the left-hand side here to then determine, sorry, Dwayne, not here, no. Okay, so your left algorithm will then determine where this line goes, your predictive line. Okay, so how you would do this is the first thing you need to do is try to figure out mathematically, and this is where this math comes in, is where to put your line. Now, best practice, and this is how linear regression works, is the line goes smack in the middle of all of your data. Okay, so you would, this is called the ordinary least squares. So this is where, based on, if you look at both sides, graph A and graph B, you'll see that in graph B, you've got above the line, your dots are quite far away from that line. Below the line, you've only got about 2 dots that are very, very close, and the rest of them are quite far away from the line. So this is where the ordinary least squares comes in. You would do the mathematics that would show you, based on where the dots are, where where the line needs to go based on how far the most of these dots are away from the line. Okay, so if you look at graph A, all of the dots, or just about all of the dots, are right on top of the line. So the line could just go smack in between with no issue. Based on graph B, the dots are a lot further away from each other, so you would have to do a calculation based on how far, based on the outer dots away from the line. Okay. Now, if we look at the mathematics behind this, the graph just below actually shows this ordinary least squares. So you can have a look. It's actually connected to that line in the middle. So you can have a look and see the very second dot from the X, from the Y vector here, and then the third last dot on that side, on the right hand side. You can see they're quite far away from each other. So, but the majority of those dots are right against that linear line. Is this making sense? So basically, in a nutshell, the line goes in between the dots that are the closest, or that have the most similar distance away from that line. Okay, if that makes any sense. So this algorithm now calculates just that. It will calculate where this line is going to go between all of those dots. So how this is going to work now is the line is M. Okay, so M equals this equation. This equation, I don't know if you guys know math at all. This would be the sigma symbol. No, Joshua. You can literally use this for pretty much any predictive modeling, from financial modeling to farming to just about anything. It would depend on what you're looking at doing. The reason I chose linear regression is because it is actually covered in the bootcamp for software engineering and the data science. And a lot of people, because we show an equation in there as well, a lot of people are very intimidated by the linear regression. They're also very intimidated by the k-means. So I just wanted to break down what the math looks like and how to read the scatter plot, because a lot of people don't get it. You know, you can explain this until you're blue in the face and they just don't get it. Ben, yeah, if you wanted to figure out the correlation between rain and crops, yes, that would be a good one. Your y-axis, which is the dependent variable, would be the crops, and that would be dependent on the x variable, which is the rain. Okay, so x being the lower, you cannot do anything about rain. So, but you can do something about the crops. So this line that's in between these dots will tell you for X amount of rain, this is how many crops you're going to get. Okay, does that make sense? Okay, cool. Right, so the math is quite simple. I don't know how well you guys know math. When I saw this for the first time, I was a little freaked out because I didn't understand all of these symbols and everything else. But if it's broken down very simplistically, you've basically got m being this line in between the dots. The equation behind the equal sign, that's how you're going to work out what m is. So m is basically, x is this bottom axis, okay? It's your independent variable. So you've got x, which is then minus the average of x. So that's the mean. So if you look at the algorithm, you've got m equals mean x times mean y. Okay, so you've got x minus the average of x. So this little stripe on top of the x, that just denotes the average. Okay, and I'm assuming all of you know how to work out the mean or the average of something. If you don't, it's basically the sum divided by the count. Okay, so then you've got the x minus the average of x times the y minus the average of y. Okay, that gives you the line. Then you've got that, this, okay, this sum of x minus the average of x and y minus the average of y divided by x minus the average of x squared. Okay, that gives you this line, this m. Okay, now b in this little function here, that is basically where this line meets the y-axis. Okay, so it's the coefficient. So it's exactly where m is going to cross y, and that is then either c as the coefficient, or in this case we've declared it as b. Still with me? Okay, so how you would work that out is literally just the average of y. Okay, in the algorithm, it's the average of y minus m. Okay, so this full equation that gave you that sloped line. Okay, so it's it's the average of y minus m, the answer to m, times the average of x. Okay, and that will give you exactly where this sloped line should start on your y-axis. Okay, everybody with me? Okay. You guys are smart, eh? Yes, Etienne, it's the y-intercept. So it's called the coefficient. Okay. That's why you'll find in some cases some data scientists will, instead of using B, they will use C because it is called the coefficient. So they'll just use C. In this algorithm, it was just declared as B. But it's the same thing, okay? Now, are there any questions that you guys might have with this? With anything in this deck? Because this is the last slide. So now it's time for Q&A. Is everybody doing the data science bootcamp, or are you guys on level 3 of the software engineering bootcamp yet? Etienne, you've got me there. I honestly don't know. Nkosi, if you're here, I know you're doing data science. Do you think you could answer Etienne's question about the Pearson's coefficient? Well, the data science guys, good luck to you. I did that bootcamp. It's quite tough. The math is hectic when you get into machine learning. So good luck with that. I do apologize for this being so short. I didn't realize that because we were late, I didn't realize how quickly I ran through all of that. So if the mentors can help answer any questions, then we are done with the presentation. Solomon, I do believe the webinar is emailed to you, but there should be a spot where you can, Nkosi, can you just tell the guys again where to download the PDF? Solomon, you will get the audio. The webinar will be emailed to you. Did everybody understand the mathematics behind the linear regression? It's very similar to linear algebra. If you understand linear algebra, and this was a simple linear regression, there's still multiple linear regression as well that works on a 3D model. So if you guys want to have a look at that, there's some very good resources on YouTube. You guys are welcome to go to the forum. I don't know if everybody has access to the Hyperion Dev forum. And if you guys want some resources on multiple regression, k-means, support vector machines, any of the main algorithms, then we can definitely help you guys out with that. Thank you so much for joining the presentation, guys. I'm going to be ending the webinar at exactly 1:45, so you guys are welcome to just stay around and chat. Otherwise, you're welcome to leave. You will definitely get a copy of this webinar. I hope it was worthwhile. Thanks for staying around, hey?